now. Okay. So welcome to our seminar. Very lucky to have Dr. Jack Valmadre presenting for us today. So he's a senior research fellow with AML at University of Adelaide. Before joining AML last year, Jack got his PhD from QUT in 2016 and was a postdoc at Oxford until 2018, and has also worked at Google Research in France until 2021. His research topics have included 3D reconstruction, few-shot learning, noisy labels, and object tracking. And today we'll be talking to us about hierarchical classification. So thanks very much, Jack.
Cool. Thanks very much, Jacinta, and thanks for having me today. So yeah, this is the topic of my talk, hierarchical classification at multiple operating points. And I'll define these terms better shortly, but just to say, if you want to interrupt me at any point, if anything's unclear, just feel free, also online. Okay, and I'd like to start first by acknowledging the traditional owners of the land where we live and work. Okay, and so we're looking at hierarchical classification. So I'm imagining something like this. So we have a set of classes, and usually in classification, we consider just like a list of mutually exclusive classes. But here instead, we're going to have classes that can contain other classes. So we have like mammal that contains dog, bear, and marsupial, and so on and so forth up the tree. Okay. And more specifically, we're considering a hierarchy which is fixed. So we're not trying to learn the hierarchy, like we're given this hierarchy over the classes at the start, and we want to like use it. We're considering trees, not DAGs. So that means that every node except the root node has one parent exactly. And I'm assuming that the children are mutually exclusive. So you can't be like fish and mammal here below animal. You could either be fish or mammal, but you can be fish and animal at the same time. In fact, if you're fish, you are also animal by definition. And also, yeah. Oh, yeah. Is that the light? No. Spots. Hey. I'll keep the audience ones. Yeah. So people don't fall asleep. Okay. Thanks for saying. Okay. And so when I looked at the literature for this problem, many people have considered like using a hierarchy to try to improve the prediction of your leaf nodes. But we're specifically considering the scenario where instead you want to predict any node in the tree. So for example, if you're unsure about the dog breed, you could predict just dog rather than a specific breed. Or you could just say mammal if you're really unsure about whether it's bear or marsupial. Okay, so a bit of motivation, like why would we consider these hierarchies of classes? On the left here, I have reasons that we'll consider today. And on the right are other reasons in general. So the first reason is like having a graceful failure. So if you have an image of something and you're not sure what it is, say it's an image of a dog and you think it might be a cat, but you're not sure. In that case, it's much better to say mammal rather than cat when it's a dog. And users will find that much less jarring to do. The second reason is it lets us quantify how bad a mistake is. So for example, again, if you have a dog, it's much worse to predict fish than to predict cat, because the fish is further away in the hierarchy. And this gives us a way to measure how bad the error is. And another reason is unseen classes. So often say you have like your training set, which has many different animals in it, but then you encounter an animal at test time, which wasn't in the label set for training. But maybe it belongs to a superclass, which you did have during training. So maybe you see, I don't know, like a snake, and you didn't have a snake in your training set, but you had a lizard, so you can say it's a reptile. So it's kind of like expanding the set of classes that you see during training by taking a bunch of classes, putting them together and saying this is a superclass. Other possible reasons, it might help you deal with long-tailed data. So often you have like some classes which are very rare, but it's likely that if you go up the tree, it belongs to a class for which you have many examples. That might help you deal with the long tail problem. One that I was particularly interested in is like object detection. So when you have like an image, because I work in computer vision, so you have an image, you're trying to detect the objects, and you detect an object, you're not sure whether it's dog or cat. Often the best thing to do for the metrics is just make two detections, one dog and one cat. But now like the number of objects is kind of wrong. And so if you're going to then use that for like object tracking, you're going to have these two objects which you have to deal with. And it would be much better to just say that the algorithm knows there's one object there and it's an animal, rather than having multiple overlapping detections. And finally, flexible annotation. So if your annotators are not sure of the specific class, then you can let your annotators label with superclasses. Or you could do some kind of active learning where algorithm says, I'm sure up to this granularity, but I need some help refining the label. So you could use it quite, it could be quite useful for annotation as well. Okay, so hopefully we accept class hierarchies are interesting to work on. And so here's the overview of the talk. I'm going to look at first just a formulation of the problem, a few baselines, and how we're going to evaluate this, which metrics to use. So this is really just background. And then I'm going to talk about the first major contribution, which was talking about how when we're predicting arbitrary nodes in the hierarchy, we should evaluate using these operating curves rather than a single operating point, which is kind of obvious if you think about it, but that's hadn't really been done before. And we'll look at how to construct these curves. And then I'm going to look at a few new loss functions, which managed to outperform the best existing methods. And then finally, a brief look at how these different methods which we're comparing behave with unseen classes. So it's kind of like an out of distribution problem. Okay, so first to go through how we're going to consider the problem. And all my experiments are going to be with image classification, just to say like image classification with deep networks, just so you know. So we're considering, we want something like this. This is our paradigm. We've got our X in, which is an image, some vector. And then we want to predict a probability distribution over basically assign a real number in 0 to 1 to every label in the graph, every node in the tree. So yeah, just one thing to note is that often when you see these trees, you might think of like some kind of decision tree or like a cascade or something. But instead here, I'm taking the vector and predicting the likelihood of all classes at once. So it's not like we're going to take a decision at the top and descend down the tree. We're just predicting a number for every node in the tree in one go. And that's kind of like makes it easier to do like optimization. We can just consider the negative log likelihood and so on. Okay, but those probabilities should satisfy some kind of structure. So we're going to predict a number for every node in the tree. And we want the root node to have probability 1. So in our case, the root node is kind of like, it's uninformative. It's if you predict the root node, you're kind of abstaining from making a decision because you're giving no information. And then what we want is for all like internal nodes, Y, we want the sum of the children to be less than or equal to the likelihood of the node. So you can see here, I've got like 0.7 is greater than or equal to 0.1 plus 0.6. And that holds throughout this tree. And you might ask why less than or equal to rather than equal to. So either one is kind of okay. Like having less than or equal to, you can consider it as like having an extra child, which is the other child. But basically we're saying that it wouldn't violate the like probability space assumption if that was a less than or equal to, because maybe we're in terms of like what we believe about the prediction, maybe we're more confident of it being animal than we are summing up all the likelihoods of the children of animal. Okay, so we want to predict distributions that look like this given an image. And so what we're going to have is we're going to consider several different methods. And what each method is going to be is like a parameterization key. So the parameterization, basically your confident is going to give you a real vector theta of dimension m, and that theta is going to parameterize a distribution. And we're also going to have a loss function, which takes a label y and a vector theta out of the convnet, and that's what we're going to optimize. And so we're going to consider several different methods where each method is like MPL triples. And the model architecture, we're not going to touch it. It's just fixed. It's like a ResNet, whatever. And often we will be able to take the loss function as the negative log likelihood of the ground truth label, but not always. Okay. So now we're going to consider a couple of baselines for these MPL triples. So the first one is like the very naive baseline. So what we're going to have is we've got our theta vector as a real number for every leaf node. The theta is in RL. We're going to take softmax over the leaf nodes. So for the leaf nodes, the probability is just the softmax over those leaf nodes. And then for the internal nodes, we're going to like recursively add up the likelihoods. So the internal likelihood is just going to be the sum over all leaf descendants. And this, by definition, is going to satisfy the constraint that we wanted. This is kind of like a naive approach. And so if we look at the negative log likelihood here, it's going to be convex when we're considering the leaf node labels because it's just log softmax, which is convex. But when if we have our ground truth labels being internal, we're going to have like a log sum softmax. So it's not going to be convex. Okay. But we don't care too much about convexity anyway these days. Whoops. Okay. The next method I'm going to consider, I'm going to call conditional softmax. And this is from a paper called YOLO in object detection. Or I think it existed before, but that's where I first saw it. And what we're going to have is for each family, we're going to have a softmax. So now our theta, we have real numbers for every node except the root. And we're going to sort of break it up into a subvector for each family, I'm calling it, like each set of children. And then we're going to get the conditional likelihood of the node given its parent. So if y is a child of u, then y given u is a softmax over the children. And then if we want to get not the conditional likelihood, but the likelihood of a label, we're going to take the product from the ancestors down to that node. So we're going to have like a product of softmaxes. And what's really nice about this is when we take the negative log likelihood, we have like negative log product softmax. So negative log product is going to be sum of negative logs. So we're going to have sum of negative log softmax. So we're going to have convex, regardless of whether the ground truth is a child node or an internal node. So that's kind of just a nice property, yeah. So this was like the motivation for getting into this problem really was because I thought this was very elegant, but people showed that basically it just gave slightly worse results, although they were only considering the prediction of leaf nodes. And so I thought maybe if you consider predicting the internal nodes as well when you're uncertain, maybe this will have an advantage. Okay. And like a final, very, very stupid baseline is just we treat all the classes as like independent binary problems. And we just train like, we're going to have a real number for every internal node. And the likelihood is just sigmoid of that number. So it's not going to satisfy those constraints. But it's like a very easy thing to implement. So we should consider it as well. And I'm using the focal loss, which is like something from object detection, which helps when you have a very large class imbalance, just to improve this method. Okay. So does that make sense? We've got 3 baselines. Yeah.
Probably don't understand everything you're saying here, but it doesn't feel like there's a representation of the loss of how badly you get things wrong.
Exactly. Yeah. Yeah. So that's going to be one of the losses I propose is considering that kind of how bad a mistake is. Yeah. So here, yeah, we don't really have that notion. We just have, it has kind of this structure a little bit where the, yeah, maybe this one's the best one. Like the likelihoods are related, but in the end, you are just trying to increase the likelihood of the ground truth labeled node at the cost of the ones which are not its ancestors or descendants. Yeah. There is some kind of structure encoded in it though. But yeah, the loss, it doesn't have it explicitly. Okay, so now to talk about how we're going to evaluate our predictions. So here I'm imagining that we have ground truth label Y, predicted label Y hat. And we want to say how bad is Y hat given that the ground truth label is Y. So the two most simple metrics are correct and exact. So correct is Y hat an ancestor or equal to Y? And exact is Y hat equal to Y? But you can see that these metrics are kind of, they're losing a lot of information because all the ancestors, so basically you would have like 1, 1, 1, 0, 0, 0, 0. So all the ancestors are equally bad and all the like cousin nodes, I guess you'd call these, are equally bad. Yeah, all the ancestors are equally good. Yeah, so these metrics leave a bit to be desired. And I'll just also mention that I'm considering that if the ground truth is an internal node, then it's correct to predict a descendant. It's always okay to predict a descendant. So basically, if the ground truth is mammal, you predicted dog, that's okay. Yeah, that depends on how the annotation was done, basically. So you can imagine that we always just, if the prediction is a descendant of the ground truth, we just project back to the ground truth. Okay. But still, these binary metrics are a little bit coarse. So what's the next thing we think of? Maybe like edge distance. This is not what I'm suggesting that we use, by the way. So the edge distance is going to be, yeah, you basically just have to go up to the lowest common ancestor, back down to the ground truth, and that's your distance. But this metric, I don't like using distances because it doesn't take into account where you are in the tree, like whether you're at the bottom or whether you're near the top. They can have quite different meanings in terms of like how many examples how many classes you're excluding or including. So instead of that, what people often use is like a precision recall. So we'll say that this is the ground truth, this is your prediction, these classes you got correct, this was a false negative, this was a false positive, right? Because this one you went too far down the wrong branch, this one you missed. Yeah. Yeah, exactly. Yeah. So that's what I'll get to as well, like how to account for the probabilities or the ranking of the nodes. But for now, we're imagining you just predict a single Y hat. Yeah, thank you. Yeah, so this is nice, but there's one more issue with this, which is that if your graph is very imbalanced, if your tree is very imbalanced, then the depths can be a little bit, can mean different things in different parts of the graph still. So what I propose instead is like the information at each node. So you look at the ratio of information in the lowest common ancestor compared to the information in the prediction and in the ground truth. So if your tree was like a perfect, balanced K-way tree, then these would be equivalent because like the information here is the negative log probability, where the P here is the prior distribution of the classes. And so in that case, it would just be like your log P would be, your P would be 1/2 to the or 1/k to the power of depth, something like that. Yeah, so this is the metric we're going to use. Basically, higher is better, and you have recall and precision. So recall is going to be this fraction, how much of the ground truth you got, and precision is going to be how much of your prediction was correct. Same as like information retrieval, yeah, binary classification. All right, so these are the metrics that we'll focus on. And the data set I'm going to consider is this iNaturalist 2021 mini. So even though it's mini, it is 500,000 images. You have 10,000 classes, so quite a lot of classes. That's 10,000 leaf nodes. And you also have a depth of 7, so there's maybe, I think there's maybe 4,000, 6,000 internal nodes, something like that. 50 images per class, so it's balanced at the leaf nodes, both in training and validation, and all the labels are leaf nodes. Okay, and the taxonomy is like a biological taxonomy, so you have like kingdom, phylum, something. Yeah. Okay, so just to review the background, because there was quite a lot there. So we're going to output likelihood for all nodes, and it should satisfy this constraint where children are less than the parent. A method has a parameterization P and a loss function L. The model architecture is fixed for all methods. We have these 3 baselines: flat softmax, conditional softmax, multi-label sigmoid, binary sigmoid. And the metrics are either correct/exact, binary, and precision recall. Okay, so yeah, you can imagine, I'll just mention one more thing with the metrics, which is that you can imagine as your y-hat moves up or down the tree, you would be, as you move up, you'll be increasing your precision by reducing your recall, because you'd be making less and less specific predictions, but you'd be more likely to be correct. Okay, so now let's look at inference. And by inference, I mean, we've got our distribution from the model, and we need to predict a single discrete label. We can't take the argmax because we would just get the root node every time. So you could take the maximum leaf, but then you're always going to have a leaf node. So people have sort of done like heuristic-y things in the past. So they often do either start at the most likely leaf and then move up until you satisfy some criterion, or start at the root and move down until you satisfy some criterion. But then you have to choose a criterion, and it's kind of a little bit open to interpretation how you should do it. And specifically, I'm going to look at this trade-off between specificity and correctness. So this is what I mentioned before, like as you move up the tree with your prediction, you're more correct, but less specific. And you can imagine if you always predict the root node, you're always technically correct because it is one of the classes in the training set, but you're giving 0 information. So that would be like, you'd be like here. And people have traditionally compared methods by saying like, here's my method A, here's your method B. Look, your method B is more correct and my method A is more specific. But perhaps if you looked at if you vary the threshold to change where you predict, you might see something like this, where actually method A dominates method B. If you choose the threshold such that your predictions have like this depth. And so, or maybe A doesn't dominate B. And so in that case, maybe B is interesting. Yeah, so we really need to know what these trade-offs look like. And so to do that, I'm proposing like a very simple inference rule, which is you take as your prediction is a function of a threshold tau. And what you're going to do is take the node y with the maximum information. You can think of this as the maximum depth. So the deepest node y, such that the probability is greater than a threshold. So as you vary this threshold, your predictions are going to move up and down the tree, because you know that the nodes which are deeper in the tree have a lower likelihood. Okay, and so we can imagine varying this threshold tau and tracing out a curve. And one interesting thing is that if we set tau to 0.5 or higher, and P satisfies that hierarchical constraint, then there's only one path in the tree which will satisfy this. Because, if I have one subtree which has likelihood 0.5 or a bit more than 0.5, there can't be another one which has likelihood 0.5 because that constraint is kind of like saying any cut in the tree has to add up to 1. And so there can only really be, if tau is 0.5, it's a special case, and you just have this single path in the tree. Okay, so we want to maximize information subject to this constraint on the likelihood. And so what we're really interested in is the Pareto set of predictions. So this is like given one example, we have many different possible labels. Each one has information of y and probability of y given x according to the model. And the set of y hats, which is going to satisfy this, which are going to be like the solution to this, are only going to lie on the Pareto front. Because if you're down here, cat, you never predict cat because poodle is more informative, like more specific and more likely. So all the labels under here are dominated by another label. And so as we vary that tau, we're basically going to walk along this Pareto front. So we're varying this tau, and we want to maximize information of y. So as we reduce this, we're going to get more and more specific. As we increase it, we're going to step back up. Okay. And this Pareto set for 2 variables, you can find it in like n log n time. You just like sort by 1 and then do like a cumulative maximum for the other. So it's like very efficient to do. Okay, and now, so this is going to be like, for each single example, we're going to have this kind of trade-off. And then we can imagine that our metric M is a function of the ground truth and the prediction. The prediction depends on tau. So basically, as we vary tau, our metric is going to be piecewise constant for each example. And what we want is the mean of the metric over the whole data set as we vary tau. So it's just like a sum of piecewise constant functions. And to add a bunch of piecewise constant functions, it's just going to be like sorting by the like list of knots or kinks or whatever they're called in the piecewise constant function, and then adding them up on the intervals in between. So this also is like a sorting problem, and we can do it quite efficiently. And this is going to let us construct basically a curve of each metric as a function of tau. So tau maps to metric of y and y hat of tau. Okay, and then we're going to do that for multiple different metrics. So for our precision, for our recall, for multiple different metrics. And this traces like a parametric curve in metric space. So here now I'm plotting recall and precision. And then as I vary tau, I'm going to move along this curve. Does that make sense? So basically we can construct these curves very efficiently, the same way as you would for like in precision recall curves, basically, by sorting them and looking at the deltas. Okay, and so now we can look at the results, what they mean. So we have here flat, conditional softmax, and multi-label. This is the binary independent one. And here I'm looking at precision versus recall. So we want to get 100% precision, 100% recall, top right. And interestingly, you see that the flat method actually completely dominates the conditional softmax, which is kind of a surprise because I was hoping that maybe the conditional softmax down here is the leaf node prediction. So I thought that conditional softmax would be worse for leaf node prediction, but maybe at some trade-off between specificity and correctness would come true, but basically dominated. And also the multi-label, like the independent method, doesn't work very well, as you might expect. And the curve I'm showing here is just the same thing, but in 2 different metrics, in correctness versus exact. And there you can see there's an even bigger gap, actually. And so just to explain these markers, so I have a circle here for the leaf node prediction. So this is as tau approaches 0. I have a triangle here for the tau equals 0.5, because from that point, it's just going up the tree as you raise tau. Whereas if you drop tau below 0.5, it's possible that your prediction sort of jumps around in the tree, which is kind of ugly because when you I imagine that when you predict like a node y hat, that's implicitly saying it's y hat and all of its ancestors. Yeah. So perhaps in proper operation, you might set tau to 0.5 or higher. Okay. So this is kind of disappointing. So now we need to look for different ways to try to outperform this flat softmax. Okay. So and I'm calling them new-ish loss functions because like I didn't invent them. Just one of them is kind of like a tweaked version of someone else's method. And one of them is like a sort of classical thing that people hadn't gotten to work with deep learning yet. Yeah. So the first method is called parameter sharing. So what we're going to do is, going back to our like parameterization, we're going to predict a theta with a real number for every node in the tree. And then I'm going to take the thetas and map them to a beta, where beta is just the sum over the ancestors of theta. So basically, I'm going to say that my real valued score for dog is the sum of score for dog, score for mammal, score for animal, score for root. Okay, so this is kind of going to put that structure into the predictions. And then, but this is still working in just the logit space, just real numbers. So then in order to get a probability distribution, I'm going to take the softmax over the leaves and add them back up again. So it's kind of like a hybrid top-down and bottom-up method, because you're adding the scores from the top down, and then you're getting the likelihoods of the leaf nodes, which add up to 1. And then you're adding up the likelihoods to get the likelihood of the internal nodes. So like this first step had been done before, taking a sum over the ancestors, but then they didn't do the second step of like predicting your probabilities by taking a softmax over the leaf nodes and adding them up. Usually they would just get the raw scores, like the logits, and like do some greedy method with a threshold on the logits. Yeah. Okay, does that sort of make sense? Yeah. It's a little bit complex, but it's kind of like, it's funny because it's really just putting a linear projection before your softmax, which constrains it to be a sum over the scores for the ancestor classes. So if you were doing like a linear regression rather than a deep model, this probably wouldn't make much difference. It might affect the like regularization a little bit, but you wouldn't expect it to have a huge difference. Okay, and the second loss is finally what Matt was sort of suggesting, which is why not have something which captures how bad y hat is for y. And so this is like a classical hinge loss, or it's actually the structured output hinge loss. So for ground truth label y and scores theta, we're going to consider all y hats which are not equal to y. Is that a question? We're going to consider all y hats which are not the correct label. And we have some c y hat, which is the cost for predicting y hat when the ground truth is y. Or you can consider this like class-dependent margin. And what we want is that when we compare theta y hat to theta y, to the score for class y hat, score for the ground truth, we want them to be separated by at least this margin c. And that c is going to depend on how bad the class is. Okay. So I tried this originally, and one disadvantage of this is that now we have to choose this C of y hat. But that could also be an advantage because it's an extra thing we can tune. But I tried this and it didn't work. And so I found a paper which proposes like a softmax margin loss. So let's compare this to the softmax loss. Usually we write log of softmax, softmax would be like exponential over sum of exponentials, but we can take that top exponential underneath and rewrite it like this. So we have log of 1 plus sum over y hat not equal to y. So this 1 is coming from when y hat is equal to y, we just have a 0 there, and it's exp of 0, so we get a 1. And we can see that this sort of resembles that, right? We have kind of this, instead of taking this is a positive part, like the hinge function. Instead of taking the positive part, we have like this log 1 plus, which is like the soft plus function. And then we're comparing the difference between theta y hats and theta y for all incorrect y hats. Okay. And so, oh yeah, exactly. So yeah, we have this soft plus, we have the differences, and we have the max or sum, like the log sum x is like a soft max. So it looks very similar. So then why don't we just put in the C y hat there? And so this is the softmax margin loss. Yeah. And for whatever reason, this works much better than this. One possible reason is that you can imagine that when you're taking the gradients back through this loss, you maybe have like more terms in there, like you have maybe a better conditioned gradient from this, whereas this is only going to give gradients back to a single theta y hat, whichever y hat is active in the max. That's my best hypothesis for why this latter one works. And so, yeah, the reason I said new-ish is because people used to do this when they were doing like SVMs, linear models. And people have used this loss for other things like long tail learning or sequence prediction. And so it's really just putting them together with deep learning that is the contribution. And I didn't say yet what we're going to use for C y hat. So I'm actually just going to use something very, very simple, which is it correct or not? So still maybe it doesn't take into account like the distances in the, in the graph, but the idea is that we want to give a greater penalty to these nodes than these nodes. This node is still the best. So it's a little bit messy because having a 0 here doesn't mean 0 margin. Yeah.
Why don't you provide your recall metric?
No, so I originally did this because I was originally looking at the correctness and correct and exact metrics, so it made sense. But yeah, I think if you were more worried about those metrics, yeah, hopefully it would work better. I forget now whether I tried it. I have to go and look back through the experiments. Yeah. What was I going to say? But yeah, I was going to say that these aren't an exact one-to-one comparison, because if you have C y hat equals 0, that's like saying you want no margin between them. Whereas in the softmax, it kind of still will like push them away from the ground truth label a little bit. So it's not a perfect analogy. But basically you're saying that these nodes are worse, these nodes are not ideal, but not that bad, and this node is correct. And now that we've gone to this structured output formulation, we don't really have probabilities anymore, unfortunately. So to get probabilities, we're going to do something pretty hacky, which is now we have like thetas for all y's in the tree. And so we have like real numbers for every node. I'm just going to take a softmax over all of the nodes in the tree. So just exponentiate them and normalize them such that they all add up to 1. And then take the sum over all descendants as the likelihood. So this is a bit like having that other class, because we have like, we give non-zero mass of the distribution to the internal nodes. And this is not really very well founded. Yeah, I originally tried a different loss function where this made more sense. And so when I tried this loss function, I just used the same code. And yeah, sort of works. Okay, so now we can add in our new methods. And so we have softmax margin in like cyan here, and parameter sharing with the softmax in pink. And that parameter sharing, I mentioned that someone had done parameter sharing before. That's the brown method. And so you can see that the cyan and the magenta, they're both getting above the flat softmax. Not all the time, but so, oh yeah. So this curve on the right is showing exact versus correct. And there you can see that since the structured output loss was optimizing for the correct metric, it gave a bigger boost when you look at those curves. Okay, so this is good news. Yeah, and what's really interesting here is that like flat softmax was really like dominating all other methods. Yeah, it's kind of surprising. Okay. So I've just got 10 minutes left, or less than 10 minutes. So I just wanted to look very quickly at unseen classes. So here's the idea. You can think of the flat softmax as kind of like bottom up. And the conditional softmax is like top down. And so kind of, we might expect that the top down approach works better for an out of distribution case. Because imagine you have like a new class, like a new mammal at test time. The bottom-up method is just going to get probabilities for a mammal by comparing it to all mammals it knows and adding them up. Whereas the top-down method actually has an explicit model of mammal. And it's going to look at all, like, it's going to distinguish between all animals and set all types of animal and say whether it's a mammal or a different type of animal. So we're going to do an experiment where we take the training set and just like cross up a bunch of classes during training. We're going to remove the label and we're going to remove the examples. So we just keep a subset of the classes during training. And then at test time, I'm going to put the examples for those classes back in, but the model can't predict the label because it doesn't have the label in its like formulation. But it could predict the superclass. So we're going to assess whether the model can predict the superclass for those unseen classes. And I'm going to break the metrics up into all classes, seen classes, and unseen classes. And the metric here is the area under that precision recall curve. And what we see is, so if we look at all methods, at all classes, actually, maybe it's better to just look at seen classes first. That's like what we were looking at before. We see that, yeah, parameter sharing is really strong. Softmax margin is really strong, 70, 70. Flat softmax is just behind 69, and conditional softmax is quite poor. But if we move to the unseen classes, so it's just computing the metrics on a subset of the test set, we see that, what have we got? Softmax margin has become really poor. And flat softmax is similarly poor. Conditional softmax is actually the second best now of these methods, despite being the worst by far before. So conditional softmax is the hypothesis that the top-down technique is better for unseen classes. And the parameter sharing, which was kind of like you add up the logits from top to bottom, and then you add up the probabilities from bottom to top, it also does still very well in the unseen classes. Okay, and yeah, why is that the case? I did a quick experiment where I just train and test a flat classifier, but I would train at one level of the hierarchy and test at another level of the hierarchy. So you might expect that like the highest numbers would be down the diagonal here because you're testing at level 3, so why wouldn't it be best to train at level 3? But in fact, what happens is it's always best to train with the deepest labels and then add up the probabilities to predict at a higher level. So in a way, it's not surprising because when you train at a deeper level, you have like more information in your training set. But I was a little bit surprised by this. I thought that maybe it would be best to train at the depths where you're going to test. Yeah. Okay. So I mean, one way to think about this is at the top, say at depth 3, maybe you have like animal versus, or maybe like mammal versus reptile. And so the class mammal is very diverse, class reptile is very diverse. So the decision boundary is very complex. Whereas if you break it down into recognizing many different types of mammal, many types of reptile, and add up all their likelihoods, maybe it's going to work better because the individual decision boundaries were simpler to learn. Or just that it's more information. Yeah, makes sense. Okay, so to review, we said it's very important, you should always use curves to compare methods, not individual operating points. We have this efficient algorithm based on the piecewise constant metrics to construct the curves for the whole data set. We propose these two new-ish losses, parameter sharing and the softmax margin. And the top-down methods seem useful for this unseen generalization. And future work potentially, it would be good to consider DAGs instead of trees because the tree is kind of restrictive in some ways. You can't have classes that overlap. Yeah, considering class imbalance, because at the moment we just have a fully balanced training set, whereas that's kind of related to the long tail problem. And those metrics based on the information seem like they would be appropriate to use for when you have imbalance. Trying to like, you could take the predictions of a classifier and try to find the optimal tree that gives the highest area under the curve. Investigating why that hard traditional max margin loss fails, applying it to object detection and tracking, looking at confidence calibration, because you're really depending, like the 0.5 likelihood is very meaningful in this context. It might be useful to look at like calibrated confidences. Another interesting one is like neural collapse, which is this phenomenon where after training, all of the class vectors become neuro-orthogonal and all of the feature vectors converge to the class vectors. It seems like that shouldn't hold for this hierarchical, like especially for the conditional softmax, because the last layer is just linear and it's got to capture the hierarchical structure. And it would be interesting to look into hyperbolic geometry for this problem as well. Okay, and that's all. So thanks very much.
We sort of had questions throughout the same.
Oh.
But do other people
Oh,
have
yeah.
questions online
Okay.
or more questions in the room? If not, I actually have one, but I'll wait.
Oh yeah, I see what you mean. Questions throughout.
Yeah.
Yeah.
Yeah, so thanks very much. Great. It is such that the labels are all in the leaves.
Yeah, exactly.
Do you think that moving to different kinds of labeling might change the way these precision recall curves look like?
I'm not sure. Yeah. I think the one difference you might expect is with the losses that are convex for internal nodes versus losses that are convex for all. But otherwise, I wouldn't expect too much change. Yeah. Yeah.
Can you please go back to the slide that had the comparison of the seen and unseen loss? Yeah, that one. So I'm just curious to know, because like the difference in the AUC between those two seems very small, but also quite small in comparison to the differences between them for the seen and for both.
Yeah.
Do you have any intuition for why that might be? And sorry, my second question related to that is like how many experiments it's based on?
Yes. So I think it's. So I'm not sure. Did I have? Oh, in the paper. No, it's okay. No, I didn't say. So in the paper, I have these curves with error bars. And so it was based, I think it was maybe 5 trials, just like, and the only random variables are like the shuffling of the training set and the initialization. Yeah. And
sorry, initialization being like how the model has been tuned to begin with? Or
exactly. And like the random seeds.
Oh,
The random seeds for the initialization of the content parameters. Yeah. Yeah. So it's not like bootstrap sampling the training set or anything like that. Yeah. But you're right that based on the 70.6 and the 70.0, I'm not sure if I'd say it's significant. I think it's more informative to look at the curves, and you can see like some of these curves are pretty close as well. Yeah. And so, I
Why do
should.
you think they're close for the unseen in particular? Do you have any,
Oh.
like, even just like a guess why you think they're so close to that particular problem?
That's a good
Is it
question.
just they're both sort of like not really sure because they're both around 50 as well. I
Yeah.
find this fascinating. I'm not trying to like pick at it. I'm just
No.
really interested in this.
Yeah, it is interesting. Yeah. And the differences in the unseen are relatively small. Yeah.
Maybe we can
Yes.
have it.
Yeah, sounds good. I think that they are working by a slightly different mechanism because the softmax margin had like a bit more of a failure. So I interpreted this 48.3 as like the softmax margin is kind of overly specifically catering to that loss for those classes. And then when you have new classes thrown in, it doesn't work as well. But yeah, I'm not sure. Yeah, so.
So anything here was about images,
Yeah.
there's a lot related to the next piece, so.
Yeah.
It's
Yeah.
related to genetics, where you
Mm,
have instead of a picture and colors, what you have is a string of text. Or it could be proteins, or it could be, especially for example, the microbiome space, so there are a lot of unseen nodes. It's really useful actually to see nodes that are further in the tree and not just the, because you never actually know that that species exists. Because now there are technologies to sequence in large amounts. Do you think in that space, this type of methods could be useful? Because,
yeah, for sure. It seems really relevant. Yeah.
because it's something that they basically do not have the classification, they never saw, they don't know how to classify all these strings, and they're not even able to match everything, and they don't even know the sequence of DNA, this piece of where it belongs to, it's the same actually organism or not, so I don't know. That's
Yeah, I think definitely. And it just reminded me that going back to the inference rule, like one thing that's nice about this is that you can be like, you can know that you're more confident at a high level and not confident at the lower level. Because you could invert this and do like, I want to maximize the probability subject to the depth being greater than a threshold. And that's like saying always predict at this depth, always predict at this depth. But this way it kind of lets you be adaptive where you go where you're confident, not just to a prescribed depth. Yeah.
because the problem is that you cannot grow these organisms in a lab, they have no idea how to isolate them. So they just took literally pieces of pieces of environments, and then they have to discover what organisms they are, then they never saw. But of course, if you have a genetic tree, maybe you can discover the root and then without actually building on the bottom.
Yeah, that would be very interesting. Yeah.
Like,
I don't know much about genetics, but it sounds really good. Yeah.
So I think we're basically out of time. Jack, what's the best way for people to contact you if they want to ask other questions?
Maybe just by email or come over to AIM, or you can send me an email and walk over to AIML as well. And yeah, happy to talk.
Thank you.
Thanks, everyone.